Welcome back to geometry. We want to continue taking a look at section 26, coordinate geometry. Now, before we get started, I just want to remind you guys that in conjunction to watching these videos, it's my expectation that you're also reading what our text says. I don't read it to you guys. That would be a very boring lecture where I just fill in the blanks. Try to give something that's different than that. So make sure that you're also reading what's actually typed on those pages, so that way you can get a full understanding in case there's any detail that I missed for some reason, or something additional, or a variation in perspective. So make sure that you guys are doing that if you haven't been already. Okay, so let's continue taking a look at coordinate geometry. And we have just kind of a random theorem followed by a couple of theorems on slopes. So first, the coordinates of a midpoint. So if we have 2 points or a line segment with endpoints given by P and Q, okay, then the midpoint of that line, or the point that lies directly between P and Q, is the point typically denoted by M for midpoint, and it's given by X plus U divided by 2, comma, Y plus V divided by 2. So it's just the average of those two coordinate values. Now, the proof of this is given as an exercise, and much like we'll see for not only that proof, but for other proofs in this section as well, sometimes it's convenient to write things instead of as x comma y and u comma v, write it as 2x, 2y, and 2u, 2v. It's still generic because we can divide any real number by 2, or we can express any real number as a product of 2 and some other number, and that's great. Right, because I can write x as 2 times x divided by 2. So if I want any particular value here at P, right, if I want a particular value for this, I just have to use essentially x over 2. So that way when I multiply it by 2, I get back x. Okay. So if I want a particular value, I divide that particular value by 2. Of course, nothing surprising about that. All right. So, parallel lines. What is the slope of 2 parallel lines, or how do they compare? Well, of course, they're equal to one another. So, parallel lines have the same slope, which is fantastic, except for there's one case that this doesn't consider. Of course, it does not consider the case where there is no slope, so we're talking about vertical lines. So parallel lines have the same slope, or both are vertical. Excellent. So let's write a proof of this. There are well, we want to consider the idea of vertical lines and not vertical lines separately from one another. So first, let's consider vertical lines. And let's let L1 and L2 be a pair of parallel lines. So we have a pair of parallel lines. If one of them is vertical, then the other is also vertical. And in particular, both of them have no slope. Or undefined slope. And that's important to us because we're comparing two lines that we already know are parallel, and then we're discussing their slope, and then we want them to match. So they're either vertical or the slopes are the same. So in this case, they're both vertical. If you wanted to emphasize the slope aspect, right, they're both undefined. Okay, excellent. So that takes care of the vertical case. Let's consider where they're not vertical lines. So suppose that neither of the lines are vertical. Suppose neither are vertical. Let's see here, then L1 and L2, our pair of lines, may be given by so we can identify L1 and L2 by an equation, right? A relationship between the x coordinates and the y coordinates that lie of the points that lie on the lines. So what I'm trying to say here is we can write one of them as y equals m1 times x plus b1, and the other one as y equals m2 times x plus b2. And that would be respectively. So the equation for L1 is this guy, the equation for L2 is this guy. So suppose further, or suppose also that the slopes are not equal to one another. All right. Well, if we do that, let's see here. If we have two y values, right? If we have two lines that we want to say are parallel, or they are parallel, if we consider one particular y value, then they both should cross through that particular y value. And they should do that at differing x values. So if we assume that we have the same y value, that would give us that m1x plus b1 is equal to m2x plus b2. Then we can solve this equation for x and find that x is equal to b2 minus b1 divided by m1 minus m2. And this works as long as m1 is not equal to m2 and assuming that they're not both horizontal lines. Okay, so the horizontal line case is ignored in this case. That's easy enough to handle. If both of the slopes are 0, then they have the same slope. So assume that at least one of them is non-zero. Excellent. So here's our x value, and y is equal to, if I were to plug this x value into the first equation, let's say, then I would have m1 times b2 minus b1 divided by m1 minus m2 plus b1. And if I were to simplify that, I would get that this is m1 times b2 minus m2 times b1 divided by m1 minus m2. But that is the same thing as if I had plugged it into this equation you would find or could find. So m2 times b2 minus b1 divided by m1 minus m2 plus b2. So that is to say, for this x value, the y value for the first equation is the same as the y value for the second equation, and that tells us, hence, right, b2 minus b1 divided by m1 minus m2, this x value, when we plug that into one of the equations, we get this, which is the same thing as the other. So this coordinate, m1b2 minus m2b1 divided by m1 minus m2, this coordinate is on L1 and L2. So L1 and L2 intersect. That is, right, what I'm saying here is if the slopes aren't the same, then of course they're going to intersect somewhere. And what we've done is we've set these two things equal to one another. So when we choose this particular y value, when we choose a particular y value, we're finding that there is a particular x value that gives that y value for both equations, but it's the same x value for both equations, which means that it's the same point on both lines, which means they intersect. But this is a contradiction. And since it's a contradiction, we must have that our assumption was wrong, in particular that m1 was equal to m2, or that it was not equal to, so they must in fact be equal to one another. Excellent. So this proof, again, it's a prose proof, so maybe it doesn't feel as formal, but it's still kind of hiding what's going on here. So this proof is essentially saying that the two parallel lines, if they don't have the same slope, then they're going to intersect. We've identified their place of intersection. Okay, it's a mess of characters here because we're leaving it in a generic form, but we have identified where the two lines intersect since they don't have the same slope, which causes a contradiction. And we conclude, hey, they must have the same slope. All right. So we won't go through the proof of it, but we can also discuss the relationship between perpendicular lines. So if lines L1 and L2 have slopes M1 and M2 respectively, then the two lines are perpendicular to one another if and only if the slopes are opposite reciprocals of one another. A little bit different way to write that would be that M1 times M2 is equal to -1. Excellent. So that is parallel lines and perpendicular lines discussing their slope. All right, so we'll return for a couple more videos yet, where we are talking about coordinatizing polygons, which essentially is just saying that we can take some of our results about triangles and some of our results about quadrilaterals, polygons in general, but triangles and quadrilaterals specifically for this section. And we can place them in the coordinate plane, give them coordinates, and then take a look at previous results through the lens of coordinates, which allows us to provide alternative proofs to what we've seen before. And that's what we'll take a look at in the next couple of videos. So I'll see you guys again soon in coordinate geometry.